sketching our graphs. Let's make a picture of our functions and our relations. When we collect data, it's useful to plot the data because visually we can see patterns. That's what we're looking for. And the type of pattern determined by the shape of the data. If then you can approximate it with a known function, then you can actually then use that function to make predictions and things like that. This is why it's so important that when you are plotting your data, your scale is nice and consistent. Because otherwise you might be led to incorrect conclusions. You don't have to have the same scale on the x and the y. That's not that big a deal, and sometimes it's not practical to. Because if your y values might go up to really, really big numbers, whereas your x values might be just small numbers, then it's not practical to have the same scale. However, on the one axis, that needs to be consistent. Once you've decided that's what one unit's going to be, you've got to stick with that on the x-axis, and same with the y-axis. Okay, so our known functions, we just need some key pieces of data and then we can usually draw them. The y-intercept is always very, very easy to find. So you substitute x equals 0 in and you'll get the y-intercept. X-intercept, similar thing, sub in y equals 0, but it may not be as easy to find. It just depends on the function, whether that one's going to be easy or not. If it is too difficult, then sometimes we just don't worry about it. But once you've got those intercepts, there's a few key points. If you know what the basic shape's going to look like, then you can draw a pretty reasonable graph. Different features of functions can be found. Different ones are specific to different types of functions. But never ever forget the most simplest way, and that is just plotting points. Right? There's nothing wrong with just substituting in different numbers and get a feel for what the curve's doing. So a table of values. Not that you actually have to draw the table of values, but just pick different numbers. Let's see what's happening for this curve. The most basic function of them all, the linear function, I guess we start with. And the most basic of the linear functions is this one here, where y equals x. The most simplest of them all. But any data that has direct variation, so directly proportional to, then it will form a straight line. We call it the linear function for obvious reasons. And when we are talking about experiments and things like that, we often use a line of best fit. Now of course, in a practical experiment, you'd be very, very lucky if all your data exactly falls on a straight line, of course, because you get variations in experiments and things like that. But that's why we have lines of best fit. We try and work out the best line that would be closest to getting all of those points. But y equals x is the most basic one. We can get every other straight line from it via simple translations, rotations, reflections, combinations of those things. We could come up with any straight line we like. How do you recognize a linear function? Well, hopefully you would by now. But we know that we'll always take this form, y equals mx plus b. Now, if I'm just physically looking at the equation, what am I looking for? Well, I see the terms have at most one variable. I mean, there might just be a constant, but at most it'll have one variable, and it's going to be to the power of 1. So that's what I'm looking for, a y and an x basically. Now, when expressed with the dependent variable as the subject, like we do up there, then we can also get information about the line. The coefficient of x turns out to be the slope. The number by itself turns out to be the y-intercept. Okay. There are a couple of very special straight lines. Ones that are parallel to the x-axis always has the equation y equals some constant number. So if we had a horizontal one going through the point 3,2, that must be y equals 2. And similarly, ones parallel to the y-axis must be x equals a constant number. Going through the same point, that would be x equals 3. So there are just a couple of special straight lines. We see questions like this. Show that 2, 4 lies on this particular line. Well, this brings up a good point about show that questions. So anytime you've got to show that question, you can simply solve it by substituting the number in and show that it works. That's all you have to do. You don't have to go and derive equation of line or anything like that. It's simply saying, hey, show it does. So all right, I'll substitute it into x plus y. And oh, look what happens. I get 6. It does satisfy the equation, so yeah, therefore it lies on the line. That's all I've got to do. 3C.